In case of CMOS, there is another power consumption that is known as dynamic power consumption. So as I mentioned at first, this static power consumption which is almost negligible, and this static power consumption is due to the leakage current of the transistor. Apart from this, in CMOS, complementary metal oxide semiconductor, there is a power dissipation. This is known as power consumption. This is known as dynamic power consumption. Dynamic power consumption. And in the CMOS, the power consumption is due to actually for this dynamic power consumption, because this static power consumption is almost negligible. So if there is a power consumption in CMOS, it is due to this dynamic power consumption. So where this dynamic power consumption is coming from? So far, whenever we discussed in our last lectures about the CMOS, we just get the connection of the ISN, but we didn't get any connection from the output to the another logic gate. That is from the next stage, or from the previous stage, nothing connected to our current stage, right? We didn't discuss about these things. But usually in the circuit, inside the circuit, there is some previous stage and also there will be some next stage. So it can be something like that. We already calculate the fan out of the circuit, right? So something like this. We connect those things. And this is very general one. Usually the only one logic circuit will not work. So there will be some previous stage and the next stage. So because of that things, there is some load capacitance at the output of the logic gate. Here there will be some load capacitance. These are the loads, and due to that, there is a capacitance that is known as load capacitance. So what this capacitance is coming from? So all the circuits are from MOS device, and in the MOS device, there is some, of course, there is an oxide capacitance, right? So it can see some capacitance here, as they are connected to the load. These are the load. So this capacitance is known as load capacitance. So it means whenever we connect the output of the logic gate to the next stage, then the input of the next stage will have some input capacitance. And typically the gate capacitance of the inputs will act as a load capacitance. Typically what? Which capacitance? The gate capacitance. Typically, I can write down here. Typically, the gate capacitance of the input will act as a load capacitance. Because this is the loads, this is my another logic gates, and these logic gates are made of some. Can you see? Is it okay? Because this one is fine. So this logic gate is made of an NMOS or PMOS. So there is some gate, and the gate capacitance is that oxide capacitance, right? The main capacitance. If you look at the transistor NMOS. So this is my gate terminal, and this is my body, P substrate, and this is the oxide layer, right? So here this is metal part, this is also a semiconductor, it's kind of a metal part. So it's a parallel plate capacitor, and in the middle we have oxide, so this is the gate capacitance. So it will see some gate capacitance on the input side, and that will be actually the load capacitance of the previous stage. So you can see some capacitance. Moreover, the interconnects between the two logic gates will also add some capacitance. So whenever we have two logic gates and we have to connect between these two logic gates. So there is some interconnection, right? And this interconnection also will create some small amount of capacitances. Okay. So because of this load capacitance, the output of the logic gate will take certain time to change from logic 1 to logic 0. Because there is a capacitance, so there will be some charging and discharging time. When there is a capacitor, there will be some charging and discharging time. So because of this load capacitance, there will be certain time required for the logic gate to go from logic 1 to logic 0 or logic 0 to logic 1. So if I have this one, so this is our CMOS, right? So we give our input A, we get our output A bar. This is a CMOS, this is PMOS, this is NMOS, this is a CMOS. VDD connected to VDD, connected to the ground. So you give A, you will get output A bar. So from logic 1 to logic 0 to go, it will take some time. For what? For that load capacitance. And this load capacitance is coming from what? From that gate oxide. Okay. So that means if you just consider there is a capacitor here, so the capacitor will charge you, right? At that time, capacitor is charging from 1 to 0, or from 0 to 1, that capacitor is discharging. So for charging and for discharging, it requires some time. So during the charging and discharging of this capacitor, there will be some dynamic power consumption across this logic. As they require some time to transfer from logic 1 to logic 0, or logic 0 to logic 1, there is some time. Maybe nanosecond, but there is some time. During this time, there will be some dynamic power consumption will take place across these molecules. So whenever there were, we can say that whenever there is a transition from logic 1 to logic 0 or logic 0 to logic 1, there will be some load capacitor will get charged or discharged. That means there will be some power conversion. Another important thing is, we already know this is not an ideal things, right? So that means it will take some rise time and some fall time. So that means whenever you can think like that, this is logic 0, then it will go to logic 1. This is logic 0. So some rise time and some fall time will be there, because it will not rise like this. No. So there will be some, moreover, there will be some finite rise time and finite fall time of the inputs. And during this time also, what will happen? As they are taking some time, we already see that in our last lecture that PMOS and NMOS will be never on at the same time. When the PMOS is on, the NMOS is off. When the PMOS is off, NMOS is on, right? But during this rising and fall time, there will be certain moment when both the transistors will turn on, or keep turning on. Because this is a transition period, right? For example, at the first moment, this transistor is on and this transistor is off. But for the next moment, when it will turn off, and it will go turn off for a few seconds, because due to this rise time and fall time, both the transistors will remain. And when this will happen, what will happen? The VDD will be directly connected to the ground. There was the static power consumption, right? In the NMOS, in the case of NMOS, that was happened. There was the drawback, one of the drawbacks, right? That's why we use the CMOS. If you want, you can design any logic gate by using the NMOS and PMOS as well. But if you just design with NMOS and PMOS, what is happening? Whenever we have this one with the NMOS, whenever is this one, when there is an on, this transistor is on, from VDD to ground, you get a short path. So to overcome this one, we just draw the CMOS here. So they will never get a short path between the source voltage to the ground. But due to that, things for a nanosecond, But very, there's like a spike, there will be very small shortcut between the source and the ground. So in this time, the current will flow from VDD to the ground. Because of that, there will be a power dissipation across the CMOS logic gate. So these are the overall power dissipation across the logic gates. One is the dynamic power source, dynamic power consumption, another is the static power consumption. Okay. Now, if we have given, for example, in the action, the circuit will be given, you have to find out the logical function. The CMOS circuit will be given, you have to find out the logical expression. Find the logical expression of the given following circuit. For example, if I draw the circuit, so this is the circuit. You have to find out the logical expression or Boolean expression. So what will be the Boolean expression for this? So you already know in the CMOS we have a PMOS and we have an NMOS, right? And the PMOS will be at pull-up network and NMOS is a pull-down network. The NMOS will pull down the output node voltage to the ground and PMOS will pull up the output voltage to the VCC. Okay. So this is the PMOS, this is the NMOS, and we already know we have two operations only, dot operations and the OR operations. So dot operations means and OR operations. So we already mentioned we can keep in mind APP, so AND operation with the PMOS and the are parallel. Then all other will be opposite. So can you get the result here? What will be the Y, output of Y? What will be the logical function of the Boolean function for this circuit?
A plus B.
A plus B dot.
Yeah? A plus B? A
plus B,
B,
whole bracket C.
this one?
Do we need a bar over that? There's no limit.
Yes, it should be a bar. The whole bar. Should be a whole bar.
Hold on. Okay? So one thing, this is the simplest way, very simple circuit. But one thing you can try with that one, as we already know, the NMOS will always pull down the output voltage to 0, right? And this is Y first, so that means Y equals to the NMOS. If you just look, whatever the circuit, you just look, focus on the NMOS. So the NMOS, the pull down resistor will always take the output voltage to the ground. That means Y is equals to always 0, right? So Y is always 0 means Y bar is equals to 1, because this is Y bar, right? Am I right? Yeah. So when we will get this Y equals to, Y bar equals to 1? When this transistor will be turned on and either this transistor will be turned on. So here we come here, we got this part, then we have two paths. Any of the path will be turned on is fine. So that means C dot A plus B. Then it is over. So that's why we get this. So this is the simplest one, but if we have a more complicated circuit, we can just focus on the NMOS and we just know that NMOS will always turn my output voltage to 0. Okay. Then we have to just find out which transistor we turn on to get the 0. So this is very simple one. If we have, instead of instead of CMOS, if we just use NMOS circuit, for the NMOS logic gate shown below, find the logic function. That means here this is an NMOS. So here we don't have the PMOS here. Instead of PMOS, we just have direct connected load NMOS. So all are NMOS. So here also, this is a pull-up network here. So this is pull-up network. Pull-up network, we have the NMOS. This is the pull-down network. So we have to find out the expression again. So again, we can use the pull-down network, y equals to 0 or y equals to 1. Then we can find out the expression. So what will be the expression for this one? So here we need to turn on this one. If we turn this one, then we need to turn on another one of these two. Then we'll get a path. Or we can get a path of these two. So we can write down this is A plus BC, right? A plus BC or A dot BC, sorry. A dot B plus C. A dot. So y bar equals to A dot B plus C, this is the part, then plus DE, right? DE. So it will be the whole part. So this is the very simple one. So yes, sir.
So whenever we have A and C around, we should get
A and C on.
yeah. So it should be connected to ground, right?
Yeah, we can get the current.
Yes, but then we have 3 transistors and we're reading this value, so it's like a voltage divider. It won't be 0 volts because we only have 1 transistor above and it's always on.
Which one?
The current source. So not
The current source, yeah.
So we have a current source and 2 transistors that are on, right? And we're reading the voltage between the top one and the second one.
Okay.
Yes, how would that be ground? See what I'm saying?
Mm-hmm. So it is
We-
always on, yeah, it is always
Yes,
on.
so it's like we have
So
3
it will be always
transistors.
be output from here, right?
Yeah, it's like we have 3 transistors and we're reading this. This won't be ground if they're all on. Yes. Yeah.
So it is always on, so we will not get this one. How we
Yeah,
get
how
this
would that
down?
be ground?
Yeah, good question.
Because I thought of it last time, like asked you, and it turns out you can't do that. You need some sort of logic.
So last time you asked me one question
yeah, that's
that.
what I was asking. I thought that would work, but when I thought about it, it looks like it wouldn't.
No, then I checked with myself also, that you asked me that if we can use just only one transistor itself.
Yeah, that's what I asked. This exactly.
Yeah.
But it looks like it won't work because you have like a
Yeah.
voltage divider between 3 transistors, so
Yeah.
it won't be connected to ground.
Yeah, then, yeah, I don't know why they give this example. Let me see, it's a good question, because it's always on, then we'll always get the VDD here. It will not connect to the ground. It will go to the ground through here load.
But if A is not, I mean, if A is off only, in that case, we'll get the output as VDD. But if A is on and C is also on, we'll have a path and it will go to ground then. Like if all the 3 are on.
If all the 3 is on, yeah, any path, if all these 3 or these 3 or this tree, any of the path is on, will get to be grounded.
Yeah, logically speaking, but the circuit, how would the circuit give us ground since we have 3 transistors? And we're wrapping this.
Yeah,
So it's
got
like
your
a
point.
voltage
It's a voltage
divider.
divider, it's just a voltage divider.
Yeah,
It's
each
just
one
a-
has
you
an
can
output
think like a
impedance,
resistor.
R out, yes, so that won't be ground, right? It will be 2 voltage 3 DCC.
Yeah. It will be some certain voltage.
Yeah, that was my question last time.
Mhm.
I asked if we could just use one current source, but it turns out it won't work. It won't get, we don't have to do that.
Okay, I will get it again.
Fine.
So because, yeah, the question here, it will be just a voltage, it will not be grounded. Yeah.
Is it just, the resistors are just, the resistors would be very small?
If it is that very small value, then maybe there will be no voltage drop.
But
So,
still.
but still, it's, as according to him, there will maybe the almost same configurations. If you just want to make that the configuration is different, that means when the on resistance, that means when the transistor is on, we call it an on resistance, right? So according to you, maybe if the resistance is very small, maybe the voltage will be very small, right? As you mentioned, if for example it is 1 kilo ohm and they are 5 kilo ohm each, then it will be different.
Yes,
The
it-
voltage drop will be very small here. But according to here, all the MOSFET are same, so they have the same resistance value.
It would only work if we had like a really smaller output impedance with the SAR, the current source.
Yeah.
And that would work. If they were the same transistors, it would.
Yeah. So I will get it, hopefully. So from here, you also get this, your question last time that can you use one transistor only? So we cannot actually use that one transistor. Okay. Now we'll move to design some other circuit, combinational circuit, as we discussed in our, at the beginning of this course. We just try to design marks, demarks, right, error circuit. So how we can design those circuits by using this CMOS circuit? The first one, I tried to design a mark circuit, a 2-input mark circuit by using CMOS. So it is known as CMOS multiplexer. So if I have a very small general 2-into-1 multiplex, 2-into-1 marks, that means it has 2 input and 1 output. So 2 input is I0, I1, and as it has 2 input, it has only one selection line, right? S1, and the output is Y. So to get the logical expression, of course, we need to go with truth table. So if I draw the truth table, the S input selection, S, and the input, I. So when selection 0, it will select I0. When selection input is 1, it will select I1. So at that case, we will get output I0, and that case we get output I1. So from the truth table, we can write down the Boolean expression for I0. It will be Y equals to I0 S bar plus S I1. So this is the logical expression. And once we have this logical expression, we can easily now draw our or design our multiple CMOS circuit, right? So we have 2 AND operation and 1 OR operation. So for the AND operation, the PMOS will be in parallel, right? And then OR operation, it will be in series. So if you just draw it, how will it look like?
So in the truth table, is it not like input, like for each selection line, inputs are same, but it selects output as
So the mux means which input will connect it to the output, right?
Yeah.
So when S equals to 0, we can say this I0 will be connected. So we get I0.
Yeah, one point is like, shouldn't we write input as like I0 I1 and I0 I1 because we consider it both as inputs, not like different inputs.
Yeah, you can. we just I0 and I1 means two different inputs, yeah? These two different inputs. So if we have this one, so now let me draw this CMOS circuit. What will be the CMOS circuit? Pull-up network and pull-down network. At the pull-up network we have PMOS, and in case of PMOS, this will become parallel, right? So these two will become parallel. This is PMOS. This is PMOS. So S bar. Then here we have I0, right? Then we have another PMOS and they are connected in series, so like this. This is S and I1. So this is the PMOS, pull-up network, this total two. And this is connected to VDD. Because PMOS is good to pass high, logic high, logic 1. Then we have to connect it to the NMOS portion. In the NMOS, if I draw the NMOS here, let me draw the NMOS here. So this will become now series. NMOS, and this will become another series. And they are connected in parallel, right? So this one S1 bar, and I0. This one is S, this one is I bar. Right? So this is my pull-up network, this is my pull-down network, this is construct with NMOS, this is construct with PMOS with the bubble. Then finally we have to take out the output. But output is again Y bar, right? Output is a Y bar. So we need to take another inverter circuit. So another inverter circuit is, we have to give it to another CMOS. Finally, Y equals to S bar I0 plus S I0. We need this inverter because a CMOS usually just gives a inverter output. CMOS is an inverter circuit. CMOS is an inverter circuit. Okay, so don't forget to keep the bubble. Okay, when you draw. So because with the bubble we can understand this is the PMOS and this is NMOS. This is pull-up network, this is pull-down network. Pull-down network will be always connected to the ground. Pull-up network will be always connected to the VDD. Let's have a, can I go? Let's have a design CMOS half array circuit. A CMOS half array circuit. So in the half array circuit, if I draw the block diagram here, we have two input and we have two output, sound and camera. Okay? Then we have the truth table here. A, B, sound carry 0, 0, 0, 1, 1, 0, 1, 1. So we'll get sound equals to 0, 1, 0, 1, 1, 0, 1, 1 1 0, it will be 0 0 0 1. From here, from the truth table, we can find easily the Boolean expression for sum and carry. For sum, it will be, so this is the sum, so A bar B, A B bar. A bar B plus A B bar. And for the carry is just A B, right? For carry is just an A B. So A bar B or A bar B bar means XOR gate, but we already know that for the CMOS it will give you the inverter, right? So we can think it's a double bar, so it will be AB plus A bar B bar whole bar XOR gate. So if you just design this one according to this expression, it will act like a sum operation for apparatus circuit. Same way for this one, for this AB bar, it will be A bar plus B bar whole bar. So you already get our expression. Now, according to the expression, you have to design your CMOS. So we have anything done. So we have two product terms and on what terms? Here also we have A and B and what terms. So for sum, it will be AB and A bar B bar, right? So AB, then A bar B bar, so it's connected to VDD. A bar, B bar. Okay? Then this is almost all the PMOS. Then we have to draw the CMOS, NMOS. In the NMOS, these two will become series. So this is AB. And these two will become series and it will be parallel with this one. This is A bar. If you take the output here, this is Y, this is sum. I can make a sum. It's to AB plus A bar B bar. So we get the sum of. So of course we have to connect to the ground here. So I make a mistake here. I should give a bubble here. I should give a bubble here. So this is the PMOS. Pull-up resistor connected to the VDD. PMOS. Bubble is there. These are NMOS connected to the ground here. Pull down network, pull up network, and output is this one. Okay. For the carry operations, we have a simple one, is just A bar, B bar, whole bar. So at first we have these two. So A bar, B bar, A bar, B bar, on operation. Then we have A bar, B bar. So it gives you the carry A bar plus B bar. So sum operation and the carry operation. So by using this CMOS, we can design the half-adder circuit. So as we can also design full adder circuit. Two half-adder circuit will give you the full adder circuit with an XOR gate, right? Sorry, OR gate. Okay. Now, can I do it? Yeah? Now we'll do one more problem. Here we have to design the circuit as well as we have to find out the equivalent W/L ratio. That means we already know this is all the NMOS and PMOS, right? And N and PMOS we have to, the most important part is the W/L ratio, the channel length. And that is equivalent to the resistance. This one control the capacitance as well the resistance, the channel, right? So here we have to find out two things. We have to design the circuit as well as find the equivalent W/L ratio of CMOS inverter circuit for simultaneously switching of all inputs. We have to find out the equivalent W/L ratio. Find the equivalent W/L ratio. Equivalent W/L ratio of CMOS inverter circuit. While all the simultaneously switching of all inputs, here they give us the assumption, assume that W/L for the PMOS is equals to 15 and W/L for NMOS is equals to 10. So we have PMOS, we have NMOS transistor, right? In the pull-up resistor, we have PMOS. In the pull-down resistor, we have NMOS. How many transistors we use? For all the transistors in PMOS, W/L ratio is 15. For all the transistors in NMOS, W/L ratio is 10. Okay. So what is the function they give to us? F equals to C plus D plus E dot A plus B. This is the function. At first we have to draw, then we will calculate that equivalent W/L ratio. So here we can see we have OR operation, another OR operation, and then NOT operation. So for the OR operation, in the PMOS, they will be connected in series. So if I just try to draw here, PMOS, 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 C, D, E, C, D, E. Then we have another A plus B, but they are all AND with this one, right? So these two will be parallel. So as these two will be parallel, this A and B. So PMOS is okay. This one is perfect. C, D, E, A, B, they are parallel. Then we have to draw the NMOS. So these two will become in parallel, these two will become in parallel, and they will become series. So if they become parallel, we can draw like this. So C, D, E, this is C, this is D, this is E. In NMOS, they are in series. In PMOS they are series. In NMOS they are in parallel. And these two are in parallel. Now these two will be in series. So this is the series connection. Then these two will become parallel. It's A and B. we already have our circuit. Now this is pull up, this is pull down. Okay, pull up and pull down. We have PMOS, we have NMOS. Now the second part, we have found out the equivalent W over L ratio. To get this equivalent W over L ratio, so we have series connection, we have a parallel connection. There is an equation for series connection. For series connection, whether it is PMOS or NMOS, for both cases. Because here you can see the PMOS are connected in series, right? And here the NMOS is connected in series. So for both cases, if they are in series, the equation of W over L, the equivalent W over L ratio is 1 over W over L1 plus 1 over W over L2, 1 over W over Ln. For parallel connection, this W over L is better. Okay, equivalent circuit is just W over L1 plus W over L2 plus W over Ln. These are the two equations. Now we have here 3, here we have 2, here we have 3, here we have 2. For our cases, I'm sorry, I'm writing here, I'm trying to write upside. So we'll just use, so for pull-up network, at first for the pull-up network, so we can see, at first look at it here, series, so CDE. So there, this is the series equation, so we can write down W over L for CDE is equals to, equation is 1 over 1 by, so for this PMOS, this is my PMOS, right? Pull-up network, PMOS. For the PMOS, W over LP is given 15. So it will be 1 over 15 plus 1 over 15 plus 1 over 15. As there are 3 only. For CDE, only this one, this way. So it is 3 by 15. Then if you just do it, it will be 15 by 3. So it will be 5. Similarly, we can find out W over L for AB. W over L for AB, it will be 1 by 1 over 15 plus 1 over 15, it will be 7.5. So you get W over L ratio for this one, you get W over L ratio for this one. Now these two again in parallel. This one parallel to this one. So for the parallel connection, you know this one, so they will just add, right? So this one we can say W over L for PMOS finally. W over L for PMOS finally. This one, this series connection parallel to this series connection, right? So it is W over L CDE plus W over L AB. So this 5 plus 7.5 is equals to 12.5. Okay? We are done with the PMOS. Now if I just, you already write down these things, can I remove? Now for the NMOS, now this is for pull-up network, that is PMOS. Now for pull-down network. For pull-down network, is for NMOS. Here in NMOS, they are in parallel, CDE in parallel. So W over L CDE is just add up, right? So for NMOS it is 10. 10 plus 10 plus 10 is equals to 30. And for this W over L AB, it is 10 plus 10, 20. Now these two parallel again connected in series. So for W over L and MOS now, it is 1 over 1 by 20 plus 1 over 1 by 30. So it will give you 12. So what we found? We finally found that for W over L by N is equals to 12, right? And W over L by P is equals to 1.5. Is it done? No. We have one more. So that means this is a CMOS, right? We just found W over Ln and W over Lp. W over Lp was 12.5 and here it is 12. Now they are connected in series, finally. The equivalent W over L. So W over L equivalent is equals to 1 over 12.5 plus 1 over 12. So finally, W over L equivalent for this circuit is 6.1. So this is the overall final equivalent W over L ratio of this CMOS circuit. So usually we need to find out sometimes the W over L ratio, the equivalent resistance, equivalent circuit. So here we are trying to find out the equivalent W over L ratio. But as well as we can also find out the equivalent load, equivalent resistance and equivalent capacitance. So I will upload the Word file. Here you can see how we can calculate those equivalent resistance and equivalent capacitance for full circuit. Okay. So just short recap here. This is the circuit according to our Boolean expression. At first we have to design the circuit. Then they ask us to find out the equivalent W over L ratio of this inverter circuit. So we can see we have series connection as well as we have parallel connection. For the series connection, we have equivalent series equations. For the parallel, also we have equivalent equations. The equation is 1 over C, 1 over A, 1 over C, 1 over D, 1 over E. Just put the value here. Number of transistor, the MOSFET. Then here we have 2 transistors. So just 1 over 15, 1 over 15, because they already mentioned W over L ratio for PMOS is 15, and W over L ratio over L ratio for N MOSFET is 10. So at first we connected for the series, this series, 5, and for this series it was 7.5. But then they become parallel to each other. For the parallel, they just be added. So 5 plus 7.5 is 12.5. So this is the overall PMOS W over L ratio is 12.5. Then this is for the pull down network, that means the NMOS. In the NMOS, this CDE is now in parallel. So we have to use the parallel equations. It's just one add up, normal addition. And we have another parallel connection of this between these two MOSFET A and B. So we have 10 plus 10, 20, because they already mentioned W over L ratio for NMOS is 10. That's why I put 10 here. Now these two again connected in series, so you have to apply the series equation equivalent for the W/L ratio. It is equivalent equation, so 1/30 plus 1/20, so it will give you 12. So this is for W/L for NMOS, this is W/L for PMOS. Now they are connected in series, so finally they are asking us to find out equivalent circuit or overall circuit, equivalent W/L ratio. Then we have to apply the series equation again. So 1/12.5 for PMOS, 1/12 for NMOS, then we get 6.12. Okay? Next, we'll talk about the CMOS transmission gate. CMOS transmission gate has some little advantage over CMOS. So it will have less power consumption, it requires less gate. Sometimes we can use the CMOS transmission gate. It's not like that we always use the CMOS transmission gate. That has the advantages. But some advantages are there, like power consumption low. And as I mentioned that they require less number of logic gates. So there are different kind of symbols of CMOS transmission gate. One is the something like this. I don't know why like this, but they have something like this. It has one input, A, one output, B. It has a control input, C, and a complementary of control input, C bar. So this is one of the symbol. Another versatile use of the symbol is something like that of the transmission gate. This one. So we will use this one. Again, the C bar. C is input, and this is output. So it has one input, one output, one control input, another is the complementary of the control input. So this is a block diagram. Instead of block diagram, what is the basic circuit? Instead of this block diagram, the basic circuit is something like that. So this is not C bar. This is C, control input, this is complementary of control input. So this is C, so this is applied to NMOS, this is NMOS, and this complementary is applied to PMOS. You can see the bubble. So this is one transistor, this is another transistor. So this is complementary, this is all true form, this is the complementary form, C bar, control input. And we have input A, and for example we have output B. So this is the basic circuit diagram of the transmission gate. So it has, the transmission gate consists of one NMOS and one PMOS, right? Transmission gate consists of one NMOS and one PMOS, and gate is complementary to each other. This is gate terminal, right? This is a source, this is the drain, source, drain. So this is the gate terminal. Gate terminal are complementary to each other, and it has one PMOS, one NMOS. So this CMOS transmission gate, basically, if we look at their working principle, it is actually a tri-state buffer circuit. If you can remember, we discussed about this tri-state buffer circuit when we discussed about the TTL, right? Transistor logic, tri-state buffer state. The tri-state buffer state means it has a high input impedance, and then logic 0 and logic 1. So this one also will act like a tri-step buffer circuit. So here, if I draw the truth table, here we have a control input, right? We have only a control input, and that is the normal input, right? C and A. Then output is B. So look at here, when control input is 0, so as they have two input, so we have 4 different configurations, right? 0, 0, 0, 1, 1, 0, 1, 1. 4 configuration. So when C is 0, control input is 0 in both two cases, right? When C equals to 0, that means C bar equals to what? 1. So when C equals to 0 in NMOS, this transistor will remain off, because in NMOS you have to apply positive gate voltage. So when C equals to 0, NMOS is off. And when it is C is 0, C bar equals to 1. In case of PMOS, you have to apply negative gate voltage, so it will be also off. If both the transistors are off, we cannot get anything at the output. So this is known as high impedance. High impedance. High input impedance. So for both these two cases, it is high input impedance. Now, when C equals to 1, C bar equals to 0. When C equals to 1, this transistor is on, because now it is NMOS, we apply some positive gate voltage, this transistor is on. And when this C bar equals to 0, this PMOS is also on. Now both the transistors on. Now we are giving our input either 0 or 1. When we give the input A equals to 0, this 0 will pass through the NMOS. Because we already know the NMOS are going to pass logic 0. That's why it will not go past through PMOS. So whenever we give the input A equals to 0, it will pass through NMOS. So we get 0, we get 0. Of course, when C equals to 1. Then when C equals to 1, when you give A equals to 1, this 1 will pass through, will go to the output through the PMOS. So it's a tri-state buffer. So this is one state, high input impedance. This is the second state, the logical 0, and the third state is logic 1. So this is known as tri-state buffer circuit. So CMOS transmission gate work as a tri-state buffer circuit. Okay? Let's design a multiplexer with this transmission gate. CMOS with the CMOS, right? 2 to 1 mask. Let's design a 4 into 1 mask with this transmission gate. A 4 into 1 mask. So as there is 4 inputs, we have to have 2 selection lines, right? We have to have 2 selection lines. S2, we have 4 inputs. They are I0 to I3, I0, I1, I2, and I3, and we have an output Y. So if you draw the truth table here, Y, sorry, we need just the selection line S1 and S2. So 0, 0, 0, 1, 1, 0, 1, 1. When 0, 0, it will be I0, then I1, then I2, then I3. So from here we can get the Boolean expression, right? So the Boolean expression y will be S1 bar, S2 bar I0 plus S1 bar, S2 I1 plus S1, S2 bar I2 plus S1, S2, I3. So we already get our Boolean expression of this point to 1 words. Now we have to implement this by the transmission gate, CMOS transmission gate. In the CMOS transmission gate, we have just one input and one selection input, control input, right? Just we saw in the this one, right? Transmission gate. We have one input, one control input, and output, right? So we have 4, so we need 4 here. So here we have input I0, I1, I2, I3. Okay? Then here at the highest level we have for these two we can see S2 bar. For this one is S2 bar. If you want to send I0, we need S2 bar, right? So for here we have to give S2 bar. If you give here S2 bar, it will be S2. To send this I1, it is S2. So I1, it will be S2, then it will be S2 bar. To send I2, it is S2 bar, I2, S2 bar, so it will be S2. And finally, to send I3, it is S2. So I3, it is S2. So it will be S2 bar. So what will be my output here? My output here will be I0 times S2 bar, right? I0 times S2 bar. Here it will be output, sorry, I had messed up here. I1 S2. Here it will be output I2 S2 bar, and here it will be I3 S2. Now if you look at the second one, in first two cases, both one is S1 bar. Both one is S1 bar. So if we just connect these two and then give it to the next transmission gate. So the selection will be, control will be S1 bar. The complement will be S1. Here we are giving output. So this one output will be what? I0, S2 bar, S1 bar, plus I1, S2 bar, S1 bar. We get these two. Similarly here, for these two terms, the S1 is common, S1. So if we just add these two and give it to the next transmission gate, here we have to give S1. So the complementary will be S1 bar. Then we will find here, this one here, right? So here we have I2 S2 bar plus I3 S2. Here we have I0 S2 bar plus I1 S2. So it will be multiplied with I2 S2 bar with S, so S1. plus I3 S2 plus S1. Then finally, if you just take these two, it will give you. So this is the 4 into 1 marks by using the transfer gate. Of course, inside we have PMOS, NMOS, PMOS, NMOS, PMOS, NMOS, PMOS, NMOS, PMOS, NMOS, PMOS, NMOS. This is the block diagram. Inside the block, we have control bar, this is input, this is output. Okay. So we can use complementary. So there are some examples here in my handouts. Very simple one, the Boolean expression. The just design the circuit by using the transmission line gate is AB plus A bar C bar plus A B bar C bar. So you have to give A input, A bar input, A input. Then here you have to give the other input. As you can give the control input here, so AB, you can multiply, right? So it will become AB. So A bar C bar, it will come A bar C bar. You ask me to draw, I can draw, or just go. I think better.
So there it is I1 just S2.
Right. So
So it's second one.
yeah. Let
I1
me.
S2.
I naught S2
It's S2 and
S1. I1.
So you have to remove the bar first. I1 just S2, sir.
Just give me a moment. I1 S2 S1 bar. Okay.
Yes.
Okay. Okay, just do one example. So the Boolean function is given like this: f equals to a b bar c plus a dot b plus ac. Design this by using the transmission rate. So here, when we have three inputs, three variables, so we can design this one like this. So you can give A here. So if you give B bar here, it will be B. So output will be A B bar, right? Output is A B bar. Then we need C. So give it to the another one. So here we need C. Give the control input C. So complementary will be C bar. So output will be A B bar C. So we can implement one product from like this. For the second, AB. So we just need one, right? So this will be A. In the control input, it will be B. In the complementary, it will be B bar. And output will give you AB. For AC, take another one. Give here C. So complementary will be C bar. Here A, so output is AC. Now you just add all these three. It will give you A, B bar C plus AB plus AC. Okay? So I have few other examples like this, you can practice. So this is all about this CMOS. We will continue about CMOS one more lecture. There we will discuss how to design the latch, the flip-flops, SR flip-flops or different other flip-flops by using the CMOS circuit. And next week. I will upload these hand notes and see there also. Thank you. Then you can just mention one, then you will just focus on one.
And we will need to. Sorry, Dr. You will need to practice examples only for writing.
Yeah.
How you doing?
Barely surviving, man.
I'm already studying for the next exam.
Yeah. I need to study too, but I'm just finishing up one of the paper.
What paper?
Conference.
You graduate in December, correct?
Huh?
You graduate in December, right? This year?
I'm graduating up in 2029.
Oh, okay.
I'm doing PhD.
Okay, I thought you finished your PhD in December.
No.
Yeah, okay.
I just joined. Not even 8 months.
Question will be not exactly same,
Okay.
but something like that.
So I'll be
Something
here
like change the values or
for a long time.
yeah.
Dang.
And we need to practice the
Those
problem.
must be so
Sequence
small.
response also.
If, as I mentioned, if you just go through the